Hey there, welcome back. In this episode of Short Text 331, I want to tell you about vector spaces and give you some examples. In a previous video, we talked about the definition of vector spaces and we discussed that in detail, but I want to tell you about some interesting examples so you can fix the ideas. So we talked about the example of R2 in a previous video with R as scalars, and so that's simply the set of vectors living on the plane like this, where the components are x and y, and x and y are real numbers. And in that case, we define vector addition in this simple way, where if this is one of the vectors and this is the other one, then you add x with x prime and you put it in the first component of the result, and y with y prime and you put it on the second component of the result. And if you define it this way, then this is of course a real number, this is also a real number, and you have a well-defined element of R2. What this tells you is simply that vector addition defined this way is a well-defined operation that will satisfy the definition of a vector space. The same with vector scalar multiplication. If q is a member of our scalar, so it's a real number, and we take our vector to be xy, then we multiply that by q by putting q right through the parentheses here and multiplying both x and y. And so q times x and q times y are going to be both real numbers, of course, and so this is also a member of R2. And as a result, then this vector scalar multiplication satisfies the definition that we need for a vector space. So this R2 with R as scalars is a well-defined vector space. You can generalize that to complex numbers. So now the entries are z and w, where both z and w are complex numbers. And you can take that together with the complex numbers or the real numbers as scalars. And in both cases, you will get a well-defined vector space that satisfies all the definition that we saw in the previous video. You can generalize that further by taking r to the m or c to the n, so objects with m components that are real or n components that are complex with the appropriate scalars that could be complex or real, and then you will have well-defined vector spaces. More generally than that, we can talk about matrices, so objects that take this form with n rows and m columns. So for example, R 2 by 2 as shown here is an example of a set of matrices with real entries. So a, b, c, and d here are real numbers. And so in that case, you would have also a well-defined vector space if you take your scalars to be the real numbers. And how do we define the addition in that case? It's the same as with vectors. We define them component by component. It's just that in this case, the components are arranged in this 2 by 2 structure or n by m structure in general. So what does that mean? It means that a goes with x and goes into the result, and b with y, and you put it in the result, and c with t, and d with r. And so this is how you obtain your resulting vector that comes from summing this guy plus this guy. Notice that I'm using the word vector to refer to this, which is an element of my vector space, even though it's also a matrix. So in this case, the matrices in the space are the vectors of the space. And that is something that's very common, and you shouldn't feel afraid of this, that saying that matrices are also vectors, that's perfectly fine. In this context, there's no problem with that at all. What about scalar multiplication? Again, the same way as with conventional vectors that are either row vectors or column vectors. So here we define it by taking our component, our element of our scalars, whatever those are. This could be complex numbers or real numbers or something else. Then we multiply our scalar by our vector in this way. We take all the elements that are inside our arrangement here, inside our matrix, and we multiply those, all of them, by our vector, our scalar q. And this, in this example, I had in mind r to the m by m or r 2 by 2, but you could think of that as working exactly in the same way for complex entries, so for matrices that have complex numbers in them. So this works perfectly fine no matter what n and m are, as long as n and m are positive integers. So at this point, I would like to say that if you like this content, if you find this series helpful, please consider liking and subscribing to the channel, as that would help us very much. This series of vectors of videos is meant for my students at the University of North Carolina at Chapel Hill. If you're not a USC student and you're looking for a tutor in physics and math, either in English or in Spanish, you can contact me at shorttakes331@gmail.com, or you can leave a message in the comments section below. So moving on to more interesting examples of vectors and vector spaces, we have spaces of functions. And one of my favorite ones is the space of polynomials. These are very useful objects in physics. And they also have very nice properties in that they're infinitely differentiable. You can take derivatives of any order of the polynomials until you eventually get 0. And in this example, I want to consider all polynomials of degree less or equal to 3. It could be any fixed number, really, but let's consider 3 for this example. And so my set of vectors is going to be the set of objects of this form. So this is going to be our polynomials. They have all degree less or equal to 3, depending on the value of D, C, B, and A. In general, A, B, C, and D are going to be real numbers in this example. And I will take the reals to be the scalars. So all the real numbers are my scalars. And once I have these numbers, then that determine a particular vector. But it could be, this number could be anything, could be any real number. And how do we define vector addition in this case? Well, it's simply polynomial addition, so it works order by order. So for example, if I take the polynomial 1 plus x plus 3x squared, and I add to that 5x squared minus x cubed, then I have to add it order by order. So the second polynomial doesn't have an order 0, so the 1 just goes right through the result. This doesn't have an order 1 either, so the x goes right through. Now I have an order x squared here and an order x squared here, and so those are added together to get 8x squared, and finally I get nothing here of order cubed, but I have a minus 1x cubed here, so that goes right to the result. And this is a result that is of course in my set of vectors right here, because the result here is 1, 1, 8, and minus 1, and that's of course a member of my vector space. And that just simply means that vector addition defined in this way, order by order, arranging things in this fashion, will give you an element of your vector space. What about scalar vector multiplication? We need a definition as well. It's very simple. It's exactly the way you would operate normally with polynomials. You take your scalar, you multiply by your polynomial, it just goes right through, and it multiplies the 2 with the 5 here, you get a 10x squared, and the 2 with the minus 1, you get minus 2x cubed, and that's your result, and that's perfectly fine. What is not defined normally when we talk about vector spaces is the multiplication of two vectors. That really, we don't talk about that, is not a part of the definition of a vector space, even though in this case, in the case of functions like polynomials, you could do it. It's a perfectly valid operation. It doesn't mean that it's invalid for the case of vectors. If you consider the polynomials as vectors, it just means that it's not an operation that is contemplated within the context of a vector space. You would need to define something more general that's called an algebra, but I'll put that in another video at a later point. And in fact, yes, you could take 1 plus x, which is a perfectly valid element of your space, multiplied by x, another element of your space, and this multiplication is meant in the conventional way. It's nothing to do with the vector space itself, but if you do that calculation, you get x plus x squared, which of course is also an element of the vector space in this case. And you would then say, oh, this is fine, this is a fine operation. Well, you have to be careful. So in this example, I use 1 plus x times x, but imagine if I had done 1 plus x cubed, that's a member of your space, and x is a member of the space, but I would get a polynomial of order 4 as a result, which is not in the space. So you see, I would run into trouble in that case. So this is part of the reason why we talked about the vector-vector product not being really part of the definition of a vector space, and it would not be properly contemplated in our definition if we take this to be our vector space, the set of all polynomials of degree less or equal to 3. Similarly, you should think about why we say less or equal to 3 and not, for example, equal to 3. How would that be a problem? Think about that and leave a comment in the comment section below if you know the answer, and we can discuss it. Why do I not just say all polynomials of degree equal to 3? Why would that fail? What's the problem with that? More generally, there are other spaces that do not necessarily involve polynomials, spaces of more general functions, and an example that comes up a lot in physics and applied math and also in engineering really is the set of all functions of the form f of x equals to a constant times cosine of x, plus another constant times the cosine of 2x, plus another constant times the sine of x, where a, b, and c, my constants, are real numbers. So this is a subspace of the type of space that you would generate with what's called a Fourier series. And we'll come back to Fourier series in a future video. But for now, let's consider this space, the space of all functions of this form, where a, b, and c are any constants that could take on any real value, and we're going to take the real numbers as scalars. So here, as with the polynomials, we will define the addition of the vectors in the same way as addition of functions. So if I have a function of this form with some constants a, b, c, then I could take another function of that form that's also in the space with different constants, a, b, and c. And how would I define the addition? Well, I just take the functions together and add them together so that I define a new function that's f of x plus g of x. And you can call this function h of x if you want, and you can show that it will have exactly the same form as before, but instead of a, I would get a plus the corresponding a for g, so a plus a prime, b plus b prime, and c plus c prime, if the primed coefficients correspond to g, for example, and you would get a perfectly well-defined element of your space. And so the addition of vectors defined in this way is perfectly well-defined, and it really takes us a step closer to showing that this V is a well-defined vector space, which it is. Similarly, for multiplication by a scalar, what do? We take the function and multiplying by a scalar is simply just go right through and multiply every term by that scalar, the real number, and you'll be fine. And so this is then a well-defined example of a vector space. So you see there are many ways to generate vector spaces that go beyond just thinking about entries in a vector. So you could define vector spaces of functions. You can even generalize this concept of vector spaces of functions where you can use any functions. It doesn't have to be cosines and sines. It could be exponentials, it could be the tangent of x, it could be all sorts of other things. And you could use even an infinite number of functions. It doesn't have to be 3 like I chose here. You could choose an infinite number of functions and you can generate a vector space with an infinite number of components in that way. And we'll talk more about that in a future video when we discuss Hilbert spaces. Now, you can generalize this further to multivariable functions. This is very important in physics, the sets of functions that have more than one variable. And this is, of course, very useful because we live in 3 spatial dimensions. And so in a lot of cases, in a lot of applications, you want to have functions that depend on all the coordinates in space and possibly even on time. And so you could consider then your vector space to be all the functions of the form f of x, y equal to a times this multinomial, if you might call it that, x times y, plus b x squared plus c y squared x, where a, b, and c are complex numbers, for example. That's a valid definition of a vector space if you attach to it the set of scalars that could be real numbers or the complex numbers. So you could prove, and it's not hard to do, that this would define, that would give you a well-defined vector space. And finally, our last example is really coming from quantum mechanics, and we're really building these concepts heading in this direction to give you the right math and the right tools that you would need to understand the underpinnings of quantum mechanics. In this example, the vector space is a set of all functions f of x, where x is real, such that the integral from minus infinity to infinity of the magnitude of the function squared is finite. So this tells us that the function is what's called normalizable if this integral is finite. And so in that case, you can define a vector space that takes you a step closer to what you would use in quantum mechanics. So this is not enough for quantum mechanics. We need, for example, a coordinate that lives in 3 dimensions, not just 1 dimension, but this would take you closer to one-dimensional quantum mechanics. But you also need to define an inner product of functions. So if your vectors are functions, then you need to be able to multiply them in the sense of scalar multiplication. That again is not a part of the definition of vector spaces. It's something more general, something that takes you to what we call an inner product space. We'll see that in a future video, but this is part of it. In order to build towards such a space where quantum mechanics lives, we need to understand how to build a vector space of functions, and this is one such example. And that's all I have for you today. Once again, if you like the content, please consider liking the video and subscribing to the channel. It would really help us. I mean all these videos to support my students at the University of North Carolina. But if you're not a UNC student and you're looking for a tutor in physics or math in English or in Spanish, feel free to contact me at shorttakes331@gmail.com, or you can leave a message in the comments section below. I look forward to seeing you in the next video.